Okay, today we're testing a claim about a mean, so we're still doing our hypothesis testing. We have to go through all the steps. So we're going to practice because there is a slight tweak to mean, just because it's statistics, there's always a tweak to it. Okay, so we have to first start by checking our requirements. And our requirements for mean is not as bad as population, or proportion, jeepers. So just like proportion, I want a simple random sample, for sure. But then the second requirement, so it's like you can have one or the other. So either we need it to be normally distributed, the sample, or our sample size has to be larger than 30. And we did see this when we were doing confidence intervals, I believe, like these were our requirements. So if it doesn't say normally distributed, can we imply it's normal distribution, or do we have to do more work with that? We're gonna follow the steps for hypothesis testing. So we'll do our null and all that fun stuff. But with mean, our test statistic is different. So remember, a mean, it follows a t-distribution, if you remember when we did that. So proportion is just like end all be all, it always follows normal distribution. Sample mean, basically if our sample is larger than 30, we can technically assume that it will be normally distributed, just because when I take a sample of a sample, it's always normally distributed. Anyways, so since it's a t-distribution, we actually find a critical t-value instead of a z-value. And so our formula for this one is x bar, which is sample mean, minus population mean, over standard deviation divided by the square root of n. And the textbook actually used this, so I don't know if that chart that I made or posted in the 8B, 1B notes, I can't remember. Remember, this little thing is the mean of the sample mean. Yeah. Which is, I think I drew a picture on the whiteboard, if our whole population is not normally distributed, but if I take a sample of 30 people from the population, the mean of every sample of size 30 will always be normally distributed. We did do that back in the day, so if it doesn't ring a bell, it is okay. Okay, so here's the thing. Instead of normal CDF today, we are not doing that. We're actually doing a t-CDF. Yay. Same thing, instead of doing inverse norm to find critical values, we're doing inverse t today. So these are the buttons we have to press on our graphing calculator to actually find our p-value and our critical values today. Okay, so let's just dive right in. Here's our example. So I recently heard someone say movies are getting too long. Seems that there are a lot of movies that are over 2 hours long. I claim that the mean length of movies is less than 2 hours or 120 minutes. Random sample of 90 recent releases produce a mean length of 108.44 minutes, the standard deviation of 17.952 minutes. Use the p-value method. Great. P-value method. All right, so get us started. I want my null hypothesis and my alternative hypothesis. And we have to figure that out based on the claim. So it says, I claim that the mean length of movies is less than 2 hours. So that means the null hypothesis is always equal to, we are using mean today. So we're using our symbol for mean, equal to 2 hours. Ooh. Instead of using 2 hours, we're going to be using 120 minutes, because my sample information is in terms of minutes. So make sure all your units are the same. Our alternative hypothesis is with our inequality statement. So the mean is less than 120. And because it's less than, that is our left-tailed distribution. Okay. We also know our significance level is 0.01. And we need to calculate our test statistic of t. So using our formula, we have t equals the sample mean. So the sample mean of 108.44 minus our population mean of 120 divided by standard deviation 17.952 over sample size of 90. And that should be a square root symbol around the 90 part. All right. So here we go. Oh, jeepers. Oh, that's fun. I got negative 6.11. Hopefully that's right. If I made my normal distribution graph, because that's what we're always comparing back to. Oh, I didn't even check my requirements. Random sample. Bam. Requirement, check. Oh, sample size larger than 30. Check. Oh, man, sorry I missed that step. I know you guys were dying to do that part. Okay, so our critical value, since it's negative, I would say negative 6.1 is like probably right there. I want to do the p-value method, so I need to find the area to the left of that. And to do that, remember, instead of doing inverse norm, or no, instead of normal CDF, jeepers, we're doing TCDF, so it's in the same spot as like our normal CDF. We just have to scroll down to the 6th option. Same thing, our lower bound, our normal distribution graph. I want to go further to the left, so negative a bunch of 9s. My upper bound is my test statistic. Remember, DF stands for degrees of freedom, so that's always one less than our sample size. So I'm typing in 89. Well, I got it in scientific notation because it's like I got it 1.2867, and it has this e to the negative 8. Like that's moving the decimal place to the left 8 times. I'm not going to write all of that out. I'm going to be lazy, and I'm going to say 0 plus instead. So that is our p-value. I should have wrote p-value, not a, is 0 plus. So I want to figure out, so is that more significant than my claim level of significance of 0.01? And we should say, yes, it's more significant. So we want to reject the null hypothesis. Oh gosh, and then we have to say follow our flow chart. I don't have that readily available. Okay, so our alternative hypothesis, claim does not contain equality. We rejected. So we would say there is sufficient evidence to support the claim that the mean length of movies is less than 2 hours. Not too shabby. Which makes sense. Okay, let's do a third example. So I want to practice the critical value method and the confidence interval method just so we have that down packed. Okay, so a college professor claims that the mean age of all college students is 24 years. Interesting. Random sample of 116 college students revealed a mean age of 22.7 with a standard deviation of 5.68 years. Use the critical value method and the confidence interval method to test the claim at a 0.05 level of significance. Okay, so our null hypothesis, alternative hypothesis. Okay, so our claim is that the mean age of all college students is 24 years. So it didn't give an inequality statement. Wasn't is more than 24 years or is less than 24 years. So we put that as our null. Is equal to 24, and this is actually our claim. Normally our claim is our alternative hypothesis. Interesting enough. So that makes our alternative hypothesis the not equal to 24, because that's the opposite. Okay, so that means if it's not equal to, this is a two-tailed distribution. So when I make my normal distribution graph, oh my gosh, I forgot to test. So what are our requirements meant? So does it come from a simple random sample? You betcha. We got random sample right there. And then, is it a normal distribution or is our sample size more than 30? We sampled 116, so our requirements are met. Can't believe I forgot again. All right, here's my two-tailed. So I have one thing on the left, one thing on the right, and I need to figure out my critical value. So this is what our graph looks like. Okay, I lost. Okay, my significance level is 0.05 is what we say, and then we have to find our test statistic. Yeah, okay. I feel like I got out of order, but I think I'm back on track. So sample mean. So they calculated a mean of 22.7 years minus our population mean of 24 divided by standard deviation, which they said was 5.68, over the square root of 1/16. So what is that? We shall see. Okay, I got negative 2.47 if we round. So that's, this guy is right there. And if we're doing the critical value method, I need to find the critical value associated with my significance level of 0.05. So this is weird. So just because it's two-tailed, I feel like it's different than what we're used to. So that means both of these areas are equal to 0.05. Both of them together. So that means this part, the area, is 0.025. If this was like a left-tailed or right-tailed, this area would be the significance level 0.05. But because it got split in half, I have to split my significance level. Yeah. Okay, so if I'm trying to find the critical value with that area, instead of doing inverse norm, which is what we're used to, we do inverse t instead, just because it's mean. So our area is 0.025 because that's the area to the left. Degree of freedom is always one less than the sample, so 115, and paste it. My calculator generated a value right there of negative 1.98. And remember, your like normal distribution graph is like a number line, so it's always least greatest. So yeah, so technically the area of that goes all the way up to negative 1.98. So then we ask ourselves, is our test statistic of negative 2.46 more significant than negative 1.98? And we would say yes. So we would reject the null hypothesis. So if we make our conclusion, we had equality with our claim, we rejected. So we will write down, there is sufficient evidence to warrant rejection of the claim. That the mean age is 24 years. Yeah, I thought that sounded weird anyway, so definitely reject that. Blech. All right, let's do confidence interval method. Okay. Just like with proportion, we need to calculate the margin of error. So I did look back into chapter 7 just to figure out what is that formula. Our margin of error formula for confidence intervals is T alpha over 2 times the standard deviation over the square root of n. Okay, so, oh shoot. Oh yeah, okay. Sorry, I got confused on our test statistic, or this critical value here. I was a little confused, but I'm back on track. So alpha is 0.05. So same thing, I am splitting it into two parts. So just like our two-tailed thing, instead of 0.05 is like one side, like this area right here is 0.025 because I have to split my significance in half to encompass both sides because confidence interval is always two-tailed. So I need to figure out what is my critical value for right there, which I did calculate that for our critical value method before. So it should be negative 1.98, and this one's positive 1.98. When we do margin of error, it's always going to be the positive value. So this is E equals 1.98 for our critical value times the standard deviation of 5.68 divided by the square root of the sample size of 116. Jeepers. Okay, let me type this in. I got out a margin of error of 1.044, I'll say. Okay, and then same thing, I have to add and subtract that to my sample mean, and the sample mean that was given was 22.7. So our population mean is inside both of these. So if I add our sample mean of 22.7 to our margin of error, I get out 23 point, I'm going to round to the nearest tenth. So then this one is 21.7. So basically the mean age of college students should fall between this. So if I was writing a statement, we would say we are, and then because our significance level is 0.05, each side of this was 0.025, so this side is 95%. 95% confident that the mean age of college students is between 21.7 and 23.7. So then we would figure out, does that support our claim? Our claim was that the mean age of all college students is 24. It does not support because 24 does not fall into that range, which is what our hypothesis test gave us. Woo! Awesome.